Bismillah ar-Rahman ar-Rahim. In the previous lecture, we discussed the addition and subtraction of binary numbers as well. Today we are going to continue that addition and subtraction of hexadecimal numbers. Okay. Let me see, there are some chat messages here. Let's see, what are they? I don't know why they are writing their IDs in the chat, but I assume that they are referring to attendance. But you have to sign up in the forum, not here, okay? All right. At the end of the lecture, remind me to give you a chance to sign up, okay? All right, so okay, attendance sheet is closed. I know, I just closed it, but I'll open it at the end of the anyway. So let's continue our discussion of hexadecimal addition, which is exactly the same as decimal addition, okay? But you need to convert the sum of every two digits to hexadecimal now. Let's take an example, okay? Let's take an example here. We would like to convert to add these two numbers here. Let me just erase the 32A in hexadecimal plus 2E8 in hexadecimal. And we would like to do the operation in hexadecimal, okay? So first of all, A plus 8, which is what? Nothing but A is 10 and the 8 is 8 in decimal, okay? So the sum in decimal is 18. So all you have to do is to convert this 18 to hexadecimal, okay? Then you get a 1's digit and a 16's digit, okay? So 18 divided by 16, this is the conversion algorithm for 18 to hexadecimal. Okay, you get 1 with a remainder of 2, and then 1 divided by 16 is 0 with a remainder of 1. So the hexadecimal version of 18 in decimal is 1, 2 in hexadecimal. So we have a 2 in the 1's digit and a 1 in the 16's digit. Notice that I say 16's digit because we're talking about hexadecimal here. The base is 16. If it was decimal, then we say the 1's digit and the 10's digit. If it was binary, then we say the 1's digit and the 2's digit, and then the 4's digit, and etc., so on and so forth. So this is the 16's digit, and this is the 256th digit, okay? All right, so 2 with a carry of 1. And then you add 1 plus 1 plus 2 is 3. And then E is converted to decimal, which is what? So 3 plus E, which is 14. Or am I wrong? Answer is going to be 17. Yes. 17, okay, which is nothing but 16 plus 1. And we know how to represent 16 in hexadecimal, which is 1 followed by a 0 in hexadecimal. Yes. So you add a 1 to that, it becomes 1, 1 in hexadecimal. So 1 and 1. Okay. So 1 with a carry of 1, right? Then this one here doesn't need any conversion because actually the result is within the even the decimal limit, okay? So the result here is 6, okay? So the answer here is 612 in hexadecimal. So the answer here is 612 in 16. Okay, use a thinner 16, okay? So any question before I show up a trick or a shortcut? Okay, so here is a shortcut instead of doing the conversion like this, like the algorithm, full-blown algorithm, you can do a trick in order to calculate the 2, assuming that the answer is greater than 16, okay, 16 or greater than 15, okay. In order to calculate the 2, you just subtract the result, which is 18, subtract 16 from the result, which is 18 here. So 16 or 18 minus 16 is 2, and there is a carry of 1, okay. So it's always, if the answer is greater than or equal to 16, then you can do this shortcut, okay. Especially if you're adding only 2 hexadecimal numbers. If you're adding 3, then this trick will not work. You have to do the conversion, okay. Okay, so so this is only applicable when adding 2 integers, not more than 2. Okay. So now we discuss or give an example of hexadecimal subtraction, although I suppose that you already know how to do that. Okay, so 3, so we would like to subtract 1d3 minus 1b5, okay, in hexadecimal. How do we do that? Actually, I'd like to use the same color here and the thinner pen, okay. So 3 minus 5, does it work?
You have to borrow.
Yeah, you have to borrow from the next stage. So if you borrow 1 from here, okay, what happens to the 3? It becomes what?
Plus 16.
Yeah, so 3 plus 16, excellent, which is 1 3
19.
in hexadecimal, right?
Oh.
So we have 1 3 in hexadecimal. So or you can just say 3 plus 16 in order to calculate it in decimal, which is what? 19, right? 19 minus 5 is what? 14.
14.
14 is what in hexadecimal?
E.
Right? Excellent. So now we move on to the next digit. D minus B. Okay, D is 13 and B is 11. Answer is 2, but we have a minus 1 here. Borrowing 1 here, right? So the answer is 1.
1.
And then 1 minus 1 is 0. Okay? So the answer here is 1e in 16. Okay? So this is the hexadecimal subtraction. It's just the same way we did it in decimal and binary. Okay? But instead of adding, like in binary, we add 2. If we borrow, in hexadecimal, we add 16. And in general, we add the what? We add the, what do we call the 16 and 2? We add the
radix.
the base. Excellent. Yeah. One more thing before we move on to the next subject is the binary multiplication. Okay? Binary multiplication is the easiest thing that you can think of. Okay? Because if you multiply binary numbers, we do the same as we do in decimal. However, you will only be multiplying by a 0, which results in a 0, or a 1, which results in the same number. Okay, so it's much easier to multiply in binary than decimal. So there is no requirement of memorizing a binary table, binary multiplication table or something. The only thing that you need to memorize is 0 times 0 and 1 times 0 and 0 times 1 and 1 times 1. That's it. Okay, and you already know how to do that, right? So now I multiply this 0 by all this number, and then below it, shifted to the left, I multiply this 1 by this number, and then below it, shifted left twice, I multiply this number by this one by this number. Okay, so for the first one, I get 0 0 0 0. Okay, 4 zeros, and then I put a 0 here because I shift left. Okay, and then for this, I copy the same number, 1 0 1 1, and then I put 2 zeros. Okay, these zeros are, if you want, you don't have to include them, but you must make sure that you add the corresponding digits together. Okay, So this bit here is added with the second bit here, not with this bit, okay? But you don't have to put these zeros, but putting them is much more, adds much more clarity. So 0, 0, and then I copy the number, which is 1, 1, 1, okay? And then I just add, that's it. Since the first line is all zeros, I just ignore it, okay? And then write the result. This is a review for your addition arithmetic. So I have a 0 at the beginning, and then a 1, and then a 1, and then a 1, and then a 0 with a carry of 1, and then a 0 with a carry of 1. Right? Let's check if the result in decimal complies with what we found out. Okay, so who can tell me what is this number? Come on, guys. It's 13. Should have memorized it now. Okay, 13 times 6, right? So 6 times 3 is 18. Let me just erase these. 6 times 3 is 18, and 6 times 1 is 6, plus 1 is 7. So all we need to know, all we need to check is that this 78 has a binary representation that is this one. Let's see. So I'm not going to use the algorithm to convert now. I'm going to use the another trick. So I'm going to decompose 78 as the biggest powers of 2 that it has, which is 64, plus whatever remains, which is what? 14, right?
8.
14. Now, I exactly know what is 14, right? Because I memorized the number from 0 to 15, right? The binary representation of the numbers from 0 to 15. So I know what is 14 in binary. Also, according to the properties that we learn, I should know this immediately. 64 is a perfect power of 2. So it's 1 times what? 1 times 2 to the 6. So it is 1 followed by 6 zeros, right? So 1 followed by 6 zeros. Okay, and 14, which is 3 ones followed by a 0. Okay, you just add these up. So this is going to be a 0, 1, 1, 0, 1, and then 0, 0, 1. Are these the same? This one here and this one here, are they the same? Yes, they are the same, yes. Okay, so they both represent 78. So the answer checks, okay? Any question? Guys, do I need to wake you up?
Clear.
So wake up, please. You said yes. Wake up. Okay. So is it easy or difficult or challenging?
Easy.
Easy.
Yes.
Excellent. I'll take your word for that.
I have to get used to it.
Okay, so let's move on. So now this is the final topic of this unit, which is basically about binary codes and ASCII characters and parity codes. Okay. So we start with the binary codes. So binary coded decimals, or in short, BCDs. Okay, BCD means binary coded decimal. Okay, the motivation to use these is that the digital system understands only binary data, and we human beings use decimal numbers, okay, or decimal digits, right? So we need a way to code these decimal digits into binary, okay, so that the computer understand them, or the digital system understand them. So BCD is the way to encode digits or decimal digits and convey the information to the computer in binary of what we need to be done in decimal, okay? So we can have either weighted codes or non-weighted codes, so weighted BCDs or non-weighted BCDs. Let's start with the weighted BCDs. In weighted BCDs, every bit is associated with a weight. Okay, so for example, this is a BCD code 8421. So the least significant bit has a weight of 1, and the second bit has a weight of 2, third has a weight of 4, and fourth has a weight of 8, just like in the normal binary numbers. Okay, this is called a binary code. Okay, binary coded decimal. Okay, straight binary coding. Okay, so for example, if you would like to represent the digit 6, using this BCD, okay, BCD 8421. Okay, so you have to find what is 6 composed of. Okay, what is the 6 is composed of using these weights. Okay, so the 6 we can write it as 4 plus 2, right? So 6 is 2 plus 4, or 4 plus 2, commutative. Okay, so it's basically we have the code here, which is 4 places or 4 binary bits, and the weights, which are 8, 4, 2, 1. We have a 1 for the 4 and a 1 for the 2, so, and a 0 for the 1 and 0 for the 8. So if you multiply this by that and this by that, add them up, you get a 6. That's what is a weighted code mean. Okay, so this is how you find 6. So if you would like to find, for example, let's say 3, for example, what would you choose for 3? Which bit are you going to turn on? You'll turn on 3, since 3 is 2 plus 1, you'll turn on this bit and this bit, and these 2 bits will be 0. Do you see that? Is it clear? Okay, let's take another example for another code. Okay, so another code will be, for example, another weighted code is BCD 84, but we have now a -2 and a -1. Okay, so BCD 84 -2 -1. So we have negative weights now. So if we'd like to represent the 6, it is going to be using this weight here, this BCD code. It's going to be 8 minus 2. So 8 minus 2 is 6. Okay, so here we have the weights, 8, 4, -2, -1. And then we set 1 for the ones that the weights that we add up. Okay, so we added up 8 and -2, right? So we have a 1 here and a 1 here and a 0 for the rest of the non-appearing weights. Okay, so this if you multiply this 1 times 8 plus 1 times -2, you get a 6. Okay, all right. Now another weighted code is BCD 2421, okay, in which we replace the 8 with a 2. Okay, so in this code, if we would like to represent the 6, it is 2 plus 4, but which 2 and which 2 is it? Is it this 2 or this 2? This is an ambiguous situation. However, some codes, okay, there are different codes available for this one. Okay, some codes use the 2 plus 4, in which this 2 is the more significant bit. Okay, for the 6. Okay, and some other codes use the lowest 2, which is this one, for the 6. Okay, it depends on which one you're using. Okay, but for our example, we're using the the most significant bit as the 2 here. Okay, so in this code, the 6 is going to be 1 times 2 plus 1 times 4 plus 0 times 2 plus 0 times 1. Okay, so eventually it is 6. Okay, now one more piece of information before we move on is that these two codes have the nice feature of that they are self-complementing codes. Okay, so if you switch these bits, the 1 to 0 and the 0 to 1, or take the complement of them, okay, so this becomes what? 0, 1, 0, 1. Okay, and this corresponds to what number? It corresponds to 4 minus 1, which is 3. Now 3 plus 6, which is the original number, is 9. So basically the 3 is the 9 complement of 6. Okay, this is what means that these codes are self-complementing codes, and this helps a lot in doing the subtraction operation. For now, do not worry about this. Okay, the concept of self-complementing codes. All I want you to know is that some codes have the feature of self-complementing, of being a self-complementing code. Okay. Okay, these are the weighted BCDs. What about the non-weighted BCDs? An example of that is XS3 code. Okay, and the code is obtained by adding 3 to the 8421 code. Okay, so for example, if you would like to represent the 6 in XS3, then you add 3 to the 6. Okay, and you get what? You get 9. So the XS3 code for the 9 is 1001. Okay, in XS3. Okay, and this equals the 9. Okay. All right, let's take a full example that is taken from the exam. Okay, so we would like to store this number here in decimal, which is 103, in memory. Okay, so we would like to specify, or we want to specify, how is it represented using different kind of codings. The first coding is BCD 5421. Okay, so how can we proceed? Who can suggest how can we proceed?
The number is too large to be stored in one.
Yeah, so we code every, remember, in BCD we code every digit alone by itself. Every digit is encoded by itself using 4 bits. Okay, in BCD. That's an excellent note. Thank you for that. So we have to use how many BCD bits in order to represent this number 103. We have to use 3 times 4, which is 12 bit. Okay.
12.
So how can I proceed now?
Yes.
Represent number 1 first.
Excellent. What is number 1 in this code, using this code?
0001.
Excellent. What about 0?
All zeros.
Excellent. 3?
0011.
Excellent. Okay. What if I say 7?
1 1010.
Excellent. Yeah. So you get the idea of weighted codes now. Okay. All right. So now what you just said, the 3 first conversions or coding, okay, are going to be concatenated with each other like this. Okay, 0001. This is the code for 1, and then this is the code for 0, and this is the code for 3. Okay, and then we put here BCD 5421 to represent to tell you that this is not a binary number; it's a binary code. Okay, in which every 4 bit, okay, represent a decimal digit. Okay, which equals, by the way, 103 in decimal. Okay. Right. What about XS3? I would like to represent this 103 in BCD XS3. What is 1 going to be?
0100.
Let's do it step by step. Okay. 1 is going to be mapped into 1 plus 3, which is
0.
Which is 1, which is 4, right?
Yes.
Yeah, 1 plus 3 is 4. 0 is going to be mapped into 0 plus 3, which is 3. And 3 is going to be mapped into 3 plus 3, which is 6. Now, all we need to do is to find the 4-bit representation of these 3 decimal numbers, 4, 3, 6. Okay? So the 4 is nothing but 0100. And then the 3 is 0011. and then the 6, which is 0, 1, 1, 0. This is in excess3. All right, and this equals 103 in decimal. What does, by the way, what does this tell us? Excess3. It tells us that this number, go ahead.
Not weighted or something like that.
Okay, it's not weighted, but again, there is a more important information here.
Okay.
What is that? It's a code. It's basically a code, okay? A binary coded decimal in which every decimal is coded into 4-bit, okay? So let's take one more example, okay? Before moving on, let's say that okay, this is in excess3. Now I would like to find the decimal that is encoded using this number, this code here. How do I come back to the decimal?
Convert every 4-bit to its
Decimal.
decimal.
Yeah, okay, this is step 1.
And subtract 3.
Excellent. In the conversion, in the encoding process, we added 3. In the decoding process, we subtract 3. Okay, so this one is going to be 6 minus 3, and this one is going to be 12 minus 3, and this one is going to be 10 minus 3. Okay, so this is 3, and this is 9, and this is 7. So the number in decimal is 397. Do you see that? Okay. Moving on.
I have a question.
Yeah, go ahead.
What if I have 2 ways to represent a number?
Okay, then you have to know. I'm giving you here. What is your question about it? Okay, fine. Well, oh, you mean like 2, 4, 2, 1?
Yes.
You'll not be given something like that in the exam, okay? Because then you need to know which one to use, okay? You need to know the exact coding table. But in the exam, usually we give you something unique, okay? It cannot happen that we give you something that is not unique without a conversion table, okay? You have to know the table to convert in order to be able to convert, okay? But if it is unique, then you can construct it yourself, okay? More questions?
Yes, I have a question.
Go ahead.
How to know which BCD to use?
You'll be given that in the question. That's the question text. Like here, for example. Convert this to BCD 5, 4 to 1. And here, excess3. That's part of the
for
question.
example, in the B part, it says BCD, but it does not specify if it's like the previous one, 5, 4, 2, 1, or
What's
the
that? Where is that?
in B part B.
Part B. It's BCD excess3. That is not weighted code. Remember, this is not a weighted code. So non-weighted code, like excess3, for example, okay, is not weighted. It's obtained by adding 3 to BCD 8421.
Oh, so it's fixed.
Yeah,
8421.
you just get the code for the decimal digit in 8421 and add 3 to that code. You get the excess3 code. Excess means addition, okay? In addition to, okay?
Yes, clear. Thank you.
All right. Again, I think excess3 has some properties that are nice, okay? But I'm not really, to be honest, I'm not really sure if it is self-complementing or not. Let's test that, okay, if it is self-complementing or not. So excess3 of let's say, let's take this example here. 3, which is, yeah, so 0, 1, 1, 0 is 3, okay? And if I complement that, I get 1, 0, 0, 1. Okay, what is the 1, 0, 0, 1? Yeah, it's not, so subtract 3. Actually, yeah, subtract 3. And 9 is 3, which is 6. So this is 6, okay? It is self-complementing. So the addition of these equals, I'm sorry. Addition of these equals 9, so it is self-complementing. So what I did is that I got one number, okay, and then I changed all the bits from 0 to 1 and from 1 to 0 here, okay, and then found out the mapping of this in XS3. What is this in what is this digit in XS3? It is 3, okay. So you just subtract 3 from that, and then you get the digit, and subtract 3 from 9, you get the digit, okay. So 3 and 9, if you add them up, you get 9. Okay, so they both, each one of them is the 9 complement of the other. Okay, so it most likely it is self-complementing code. We have to check for all the cases as well. But from this example, it appears to be a self-complementing code. Okay, we can double check later. Okay, or you can double check yourself. I don't care actually. For this course, we don't care. Okay, moving on. Here is a big warning here. I want you to not confuse coding, like BCD coding, with base conversion. Do not confuse that, okay? Coding is something and base conversion is something else, okay? So let's take an example about this. So we would like to convert 54 in decimal to binary, okay? So note that 54 is nothing but 2 to the 6, which is 64, minus 1, 63, okay? And then minus 9, okay? So 63 is this one here. Minus 9 is this one, okay? Just subtract, you get this number, which is 54, okay? Or you can use the algorithm that you know already, okay? For the conversion, which is the division by 2 and collecting the remainders, okay? But this is a shortcut for me, okay? So this is what? This is the result of the conversion. So this is the binary representation of 54 in decimal. Let's see the code XS3, for example, the BCD 8, 4, minus 2, minus 1 code for 54, okay? So the coding now is performed for every digit by itself, okay? So now we see the code for 4, and then the code for 5, and then concatenate them together and get the result. This is no way is going to be equal to this, because this is 6-bit, whereas the conversion process is at least 7-bit, or probably something, not at least. It's exactly going to be 8-bit, okay, with some zeros probably padded to the left. So now using 8, 4, minus 2, minus 1, the 5 will be 4 minus 1, which is nothing but 0, 1, 0, 1. So this is 4 is here, so here, and then minus 1 is here, so it's here. And then the 4 is, okay, so 4 is here, okay, so 0, 1, 1, 0, 1, 0, 0. Okay, so we have 5, which is 0, 1, 0, 1. And then the 4, which is 0, 1, 0, 0. Okay, notice that it is the same code as 8421 as well. Okay, why? Because we didn't need to use the minus 2 or minus 1. Actually, we did. It happens to be the same code as, I think, yeah. I think I made a mistake here. Didn't I? Yeah, I did. Actually, this is a mistake here. So the 8 is 8. I mean the 5. I'm sorry, the 5. Okay, is what? Who can tell me what the 5 is? It's 8.
8 minus 2 minus 1.
Excellent. Which means it's translated to 1
1 0 1.
1 1. Excellent. Yeah. And the 4 is the same here. Okay. So the 5 is going to be 1 0 1 1. Okay. Concatenated with 0 1 0 0. Okay. This is in BCD 8 4 minus 2 minus 1. Okay. Now compare this with this. They are totally different. Okay, totally different. This is 8-bit, at least, and this I mean, at least this is 8-bit, and this is 6-bit. Okay, so they are different. Okay, so code, I mean, base conversion and coding are two different things. Okay, do not confuse them. Any question? Okay, let's move on. Okay. So now the question is, if we want to, in addition to digits, we want to encode also letters and symbols, okay? Then what do we use? We use basically what is called the ASCII standard or ASCII characters, okay? There is a standard in which every character or digit or number or alphanumeric number, okay, alphanumeric digit, okay, or symbol is or have a code, okay? So the standard ASCII, there is a standard ASCII which is 7-bit per code per character, and there is the extended ASCII which uses 8-bit per character or characters. Okay. Let's take an example about this. So given that ASCII code of A is 4-1 in hexadecimal, and 0 is 3-0 in hexadecimal, we would like to encode this message here, COE 202, in ASCII. Okay, so we can use either extended ASCII or standard ASCII. If you use standard ASCII, then every every hexadecimal code is going to be assumed to be 7-bit. If we use extended ASCII, on the other hand, and then every hexadecimal code is going to be assumed to be 8-bit. Okay. Now, how can you use this piece of information here? A is 41 and 0 is 30. Okay. So you must understand that in ASCII, the digits are stored consecutively in consecutive codes. Okay, so the 0 is 30 or 30, I'm sorry, in hexadecimal, and then the 1 will be what? 31, and then the 2 will be 32, and so on and so forth. Okay, the same goes for the letters, though, capital letters. The big A is going to be 41. The big B is going to be 4-2, and so on and so forth. So the big C is going to be 4-3. Okay, so we have to find the codes for C, O, E, and then the code for the 2 and 0, and then there is a repeated 2 here. It happens to be, okay, 4-3. This is the code for C, and then this is the code for O for F. And then this is the code for E for 5, and then 3-2 for 2, and then 3-0 for 0, and then 3-2 for 2 again. Okay, you got it? So this can be converted also to binary as well, but too much for binary. Okay, so this is so now you appreciate the value of having hexadecimal, right? It's a compressed form of binary. Okay, Okay, moving on. So now you have we talk about error detection. Okay, so we have a sender which is a digital circuit, and a receiver which is another digital circuit. So you can think of, for example, a keyboard, okay, and a CPU or a computer, okay, a keyboard and a CPU, all right, in which there is a channel between them, for example, a USB, okay, and there is, once there is a channel, there is a chance to get some noise from the environment, okay. So the noise, what does it do? When the sender sends some messages to the receiver, okay, the noise can corrupt these messages, okay? And in order to be able for the receiver to detect corruption or message corruption, we add extra bits. We add extra bits to allow the receiver to detect error. We call these extra bits the parity bits, okay? We have two kinds of parity, either even parity or odd parity. In even parity, we add the parity bit so that the number of ones is even. And in odd parity system, we add the parity bit such that the total number of ones is odd, okay? We don't care about the number of zeros. We care only about the number of ones, okay? So here is an example. So we have a sender that wants to transmit this number to the receiver. 1101011, okay? Indicate the value of the parity bit if we use even parity and if we use odd parity system, okay? So here we go. For even, we add the parity bit, okay, such that the total number of ones is going to be even. So we have the message, the original message here, 1101011, okay? And then here for the odd as well, we have the same message. Okay? All right. So for the even, we have to add a parity bit. And for the odd, we have to add a parity bit. Okay? If you're using an even parity, we add some bit, and if you're using an odd parity system, and we add another parity bit. Okay, so who can tell me what the even parity in the even parity system? What should be the extra bit, the value of the extra bit, and why?
1.
Somebody is saying it's a 1. Why is that?
Because it's odd. Ones.
Yeah, so because we have in the message, we have an odd number of ones, and if we turn on the parity bit, we get a total number of ones that is what? That is even, which is what we want. We want an even parity, right? And in the odd case, it's the other way around, right? It has to be a what? A 0, right? Because the number of ones is already odd, so we don't want to alter that. We want to keep it odd, okay? Because we're using an odd parity system. Is that clear?
No, doctor, don't get it.
Okay, well, what's not clear here?
Why the 1?
So this is given here. Okay, do you know that this is given? Yeah.
Yes.
This is the message. I want you to count the number of ones in the message.
Yes.
How many ones are there?
5.
5. Is it odd or even?
Odd.
Okay, so we're using an even parity, so odd doesn't work for us, odd number of ones. So we add a parity bit to make the total number of ones even. So do we add a 0 or a 1?
A 1.
A 1, okay? So you get it now, right?
Yes, yes.
Okay, great. Okay, so here is an exam question. We have an 8-bit binary code for the character C, which is this one here. All right. It's basically the ASCII character for C, right? Use even parity, yeah, or using even parity, the sender inserts an extra bit that is equal to what?
1.
It has to be either a 0 or a 1, but we are using an even parity.
1.
1, why?
Because it's even parity.
So the total number of ones becomes 4 instead of 3,
4.
right? Yeah. All right. Now it says, continue the question. It says the receiver receives 9-bit binary code that is equal to this code here. Okay. Would the receiver detect an error?
Yes.
Yes.
Why? Why?
Because he added 0.
No, this
When,
is not the answer. Can you
when
convince
it's
me more?
Even parity, he added 0. We have 3 ones.
Yeah. So because the message contains how many does it contain even or odd ones? It contains odd ones, whereas we're using even parity. Okay. This is why. Okay. Get it?
Yes.
Okay.
Yeah.
Cool. All right. I think I'm going to stop here and then pose for your questions. So I think there are people who missed the attendance. So please, if you missed the attendance at the beginning, do not leave until I take your attendance. Okay? Do not leave. All right? Yeah, Shuaib and Abdul Malik. Yeah? Do not leave until I and also Cindy. Okay? So let me just stop recording.